center mass is in chapter 10 or chapter
9.
It's in 9.
Yep. Okay, so on last week we covered center of mass. X center of mass is x sub I, m sub I over summation of m sub I. Y center of mass, y sub I, m sub I over summation of m sub I. And then the integral version of those equations are these ones. Integral x dm over integral dm, integral y dm over integral dm. The kind of problems that we focused on were the ones that you don't need to integrate, such as you have a sphere and a rod, and we found the x center of mass of that. And then we took a letter such as the letter F, and then we found the x center of mass and y center of mass of that. So while we're doing this, let's also introduce chapter 10, which is the torque moment of inertia and rotational kinematics, dynamics chapter. So with the rotational kinematics and dynamics, and the torque is part of that, and moment of inertia is a huge part of that too. So what we do is we're analyzing the motion of an object that's turning, right? And then so we go like this, let's say a cylinder or a sphere, and we say, okay, if the object is turning, the distance traveled along the edge of the object is s, and this is the radius of the object, and this is theta. So s is equal to r theta. So that relates the distance along the edge of the object to the angle that it turns through. Then if we differentiate that, we say v is equal to ds dt. That's equal to r d theta dt. So v is going to be the tangential velocity of the edge of the the tangential velocity at the edge of the object, that we call v tangential. And then d theta dt is omega, is the radians per second.
Mm-hmm.
So we have v tangential is r omega, and we have if you differentiate that one, then you're going to get a tangential is the rate of change of the v tangential. That's equal to r dw dt, and that's equal to alpha. So this is going to be in radians per second. This one is going to be radians per second squared. So omega is going to be angular velocity, and then alpha is going to be angular acceleration. Right, and then you introduce the whole topic of rotational kinematics. So you see how we have the equation v is v0 plus at. And then we have the way that they derive the first equation is they're basing it off of the linear equation. V is the velocity at the tangent of the circle, right? So that it says v is equal to r omega, right? So they're using this equation. V tangential is r omega. So then r omega final, and then v0 is going to be r omega initial, right? Plus, and then a is what? Then a is equal to r alpha, right? So you're always using these three equations to relate. These are linear quantities. You're relating linear quantities to their angular quantities, right? So then A is equal to R alpha. So they should put it here alpha. And then R cancel. Then you get the first equation of rotational kinematics. So V final is equal to V initial plus AT. But remember, this is not a general equation. This only applies when what? When the acceleration is constant, right? So when A is constant. So then this equation that they derived, omega final is omega initial plus alpha t. That's also going to apply when alpha is constant, the angular acceleration. So when alpha is constant. Right? So you would apply the same techniques when if A is not constant. How do we derive the equation for the V? We do an integral, right? Well, if A alpha is not constant, then we would use the same techniques to derive the omega equation when alpha is not constant, right? So then you have here the other equation for kinematics is what? X is equal to the initial x t plus half a t squared, right? X final is equal to x initial plus this one here, the initial t plus half a t squared. And again, that applies when the A is constant. So then you would replace what? X gets replaced by what? The position, the angular position of the object, right? So almost like you're trying to imagine as if there's a dot on the object and you're positioning that dot. So as it's turning, its position, its angular position is changing, right? Theta is changing. So X gets replaced. X is sort of like your linear position, and then theta is your angular position of that dot. So the angular position is omega initial t plus half alpha t squared. So then that's this. And then the next one is going to be B final squared is B initial squared plus 2ax. Okay, and then that gets replaced by omega final squared is omega initial squared plus 2 alpha theta final minus theta initial. So as long as you remember A gets replaced by alpha and X gets replaced by theta and B gets replaced by omega, then all of that, so you're introducing new equations but not really new equations. Okay, that's good. They give a good example. Let's see here. Deep sea fisherman hooks a big fish that swims away from the boat, pulling the fishing line from his fishing reel. The whole system is initially at rest, and the fishing line unwinds from the reel at a radius of 4.7 centimeters from its axis of rotation. Right? When you go fishing, that reel that you have, right? It's unwinding. The reel is given an angular acceleration of 110 radians per second squared for 2 seconds, as seen in figure 1. What is the angular velocity of the reel? At what speed is fishing line leaving the reel after 2 seconds elapses? How many revolutions does the reel make? How many meters of fishing line come off the reel in this time? So these are all rotational kinematics questions. It's not dynamics. Why? Because we're not dealing with torques yet. Torques, moment of inertia, all of that. We're just dealing with motion, right? So you're given the radius of the motion. radius is 4.5 centimeter, right? And then the angular acceleration is 110 radians per second squared. And then the time is 2 seconds. And then what is the angular velocity of the reel at 2 seconds? Right? So how would we solve that? Omega final is omega initial plus alpha t. Alpha is 110. This is 2. So omega final is going to be what? 220 rads per second. Right? So that's the angular velocity of the reel at 2 seconds. B, what do they want to know? At what speed is fishing line leaving the reel after 2 seconds? So what is the speed? In other words, is that they want to know the tangential speed at the edge of the reel, right? V tangential. So how do we do that? R omega, right? So since we know omega, we multiply that by R. My R is what? 4.5 centimeters. So change that to meters. 0.045, right? Go back 2 spaces, and then multiply that by 220. What is that?
9.9.
Hmm?
9.9.
9.9, okay. The numbers they're giving us are probably realistic numbers. That's why I like seeing sometimes questions from online, because when I do it, I'm just sort of randomly giving you numbers, but I don't know. But here's more realistic numbers. So that would be the approximate angle, the alpha of a fishing line, I guess, as it's unwinding. It sounds pretty fast, radians per second squared, but, and then this sounds pretty fast too. This is the acceleration, and then this is the velocity, the angular velocity, right? Then see how many revolutions does the reel make during that time, okay? So how would we calculate that?
If you get the S equals R theta,
S is R theta.
and then
Well, no, revolutions is more
Turns.
angles, right? Turns. Well, I guess you could do
Yeah, I
S
was
is
gonna
R
say
theta, but
that
that would get, that's
divide.
gonna give you meters.
and then you would divide by
Yeah, or why don't you directly get this one? How about this one? Right, and then omega initial is 0, theta initial is 0, just do half alpha t squared. That would give you the angle, right? Half alpha t squared. 110, 2 squared. Right? 220 radians. So that means it has turned the fishing thing has turned 220 radians.
also need to divide by 2 pi.
The reel, right? Then you can do 2 pi radians is 1 revolution. Right? Okay, about 35 revolutions. D, how many meters of fishing line have come off the reel in this time? I like it because it's very good progression of questions. How many meters? Well then, now you do S star theta. That's how many meters of the line have come out. But then you wouldn't multiply it by 35 revs, just multiply it by 220 radians. Because this is This is gonna be units of meters. You have to multiply it by units of 220 radians, right? And radians times meters gives you meters, because radian is not really a unit, you know. So this times this, that's gonna give you 9.9 meters, right? So it's actually, S and V are the same, because omega and theta were the same. They were both just 220. That's kind of a coincidence. I don't think that's always the case. 9.9 meters. Let's see if our answers are right. You see, that's the other thing that I did here that's cool is I didn't look at the answers. I did the thing, and then I checked to see if I'm right. Because what a lot of students might do is look at the answers and say, oh yeah, it's making sense, and you're cheating yourself. That's making sense because of course you're watching somebody else do it, you know. You struggle through it, then look to see if you're the same, and then see if it's making sense, right? You're cheating yourself. So 220, 9.9, 220 radians, 35 revs. There you go. And then 9.9 meters. Well, now they show the picture. You see here? The radius, rotational quantities, theta, omega, alpha, and then a fishing line, and then those are the linear quantities. How many meters have come out? V is the speed at which they're coming out, and A is the acceleration at which they're coming out. Let's see. Yeah.
So for the to find the velocity in like a rotation
Yeah.
we have to substitute or switch out the velocity with the omega, right?
Exactly. Yeah. Well, in the rotational quantities, you could do in theta, omega, and alpha. So in this problem, they already gave you the alpha, and they gave you the time, and then you're working with these. So you're either working with this, this, and then if they would ask for a linear question, then you're translating it using these to linear quantities, S, V, and A. That translates it to linear.
And when we're looking at the tangential velocity, we're looking at the
That's
fishing
the
line
V.
coming off the reel, right?
Exactly, that is
So that's the
tangential.
linear.
Yeah,
Okay.
yeah. That's the tangential velocity, yep. So it says now let us consider what happens if the fisherman applies a brake to the spinning reel, achieving an angular acceleration of negative 300, right? After a while, you're supposed to be applying a brake because you don't want it to keep going, right? You go like this. So then the acceleration is negative 300. How long does it take the reel to come to a stop? How long does it take the reel to come to a stop? So then it's kind of like asking the question E. So then you're gonna do, this is gonna be 0. Omega initial is gonna be 220 minus, what was it, 300 T. So T is gonna be 220 over 300. Right, so that's pretty easy question. 0.733. Calculating the slow acceleration of trains and their wheels. Okay. So large freight trains accelerate very slowly. Suppose one such train accelerates from rest, giving its 0.35 meter radius wheels an angular acceleration of 0.25. After the wheels have made 200 revolutions, assume no slippage, how far has the train moved? What are the final angular velocity of the wheels and the linear velocity of the train? So these are really good rotational kinematics problems, right? Okay, see if you can get it started. Get it started, then I'll join in. They gave you the radius of the wheels, They give you the angular acceleration. That would be the first thing I do, right? Data, find out how many radians it has turned. Far has the train moved. And then you can do S is equal to R theta. $439.82 meters, right? Yeah. How far has the train moved down the track? What are the final angular velocity of the wheels? So they want to know omega final. And then its linear velocity. They want to know v final. Right? So then omega final, then you can do your alpha t, right? Oh, there's no t, hold on.
Yeah, you gotta get it from the data initially.
Oh, yeah, yeah, hold on.
Or have the data final equation.
You could do it using this equation, right? Hold on, omega final, yeah. Omega final squared is 2 alpha theta final minus theta initial. Yeah, there you go. Because they didn't give you the t, right? Just like back in chapter 2, sometimes you don't know the t, you use this equation, right? So they gave you that one, so then you just do 2 times alpha, 0.25, and then theta final is gonna be your 1,256.637. And then of course theta initial is just 0. Okay, so omega final is that. Then once we get omega final, okay, what is the find the linear velocity of the train? V final is gonna be omega final times r. Now notice that this serves two purposes. It not only gives you the V final at the tangential V final of the tip of the tires, but it actually gives you the V final of the train itself. You see? So it serves two purposes. Notice the way that they worded it. They didn't say find the final linear velocity of the tip of the tire. They said find the final linear velocity of the train. But they're the same. They're the same if there's no slipping happening. Right? So in other words, if this is a train, this is the tire, see V tangential, V tangential, V tangential, V tangential, right? But the train's velocity is also the same as the tangential velocity of the tires. That's right? So right, when we're doing omega final r, that's giving us V tangential of the wheel. But that's also equal to the velocity of the train by induction, you know. So this is equal to V of the train. And so that's equal to this times the radius of the tire . 8.77 meters per second.
Does that mean that the acceleration tangential would be the same as the acceleration of it?
Yeah,
Oh, wow.
yeah. If a car is on an incline and it's accelerating, the acceleration at the tires should also be the same.
So sometimes like in the bottom, aren't they pointing like in the opposite direction?
Yeah. Now this is taking us to the whole section of rolling motion, which we talk about rolling motion, but we have the velocity of the center of mass of the tire is equal to the V tangential. And the center of mass of the tire is also moving at the same velocity as the train. So that means the contact point has a total velocity of 0 when something rolls.
Yeah, alright, that's what I was saying. And at the top it would be like double.
Double the velocity, yeah.
I
The top has double the velocity, the contact point is not moving.
So like in wheels, like the
Those are called pure rolling motion, no slipping, right? No slippage. Yeah, exactly. They're all equal. If it's pure rolling motion, then no slipping is happening, the two are the same. Microwave food, direction of rotation. A person decides to use a microwave oven to reheat some lunch. In the process, a fly accidentally flies into the microwave and lands on the outer edge of the rotating plate. That's nasty. Remains that if the plate has a radius of 0.5 meters and rotates at 6 RPM, calculate the total velocity traveled by the fly, the total distance traveled by the fly, during the 2-minute cooking period. Right? So they're using this also to explain how to deal with unit RPM. What does RPM means? Revs per minute, right? Revolutions per minute. So how do you go from there to, how do you use that to do what with that? So then revolutions per minute is closely connected to the omega, which is radians per second, right? So it's good to be able to deal with RPM sometimes. In some
It's runs per
problems.
minute.
Yeah, so in that kind of a problem, you're gonna go 6.0 revs per minute. Then you're gonna go 1 rev is 2 pi radians, and 1 minute is 60 seconds. And you're gonna have 6 over 60, that's gonna be 10. So 2 pi over 10. So that's 6.28 over 10, 0.628 radians per second. So 6 RPM changed into 0.628 radian per second. And what quantity is that? That's your omega. So if the plate has a radius of 0.15 meter and rotates at 6 RPM. So in this case, what is the alpha? The alpha is 0. There is no angular acceleration. So for all the questions before, there was a certain alpha. In other words, the rate of rotation had been changing. But in a microwave, the rate of rotation is constant. So it's just, it's not speeding up. It's just one rate, right? So in that case, it says calculate the total distance traveled by the fly. So what equation do we use then if there's no alpha? Well, this disappears, right? And if there's no alpha, this disappears. So the only equation is this. Theta is equal to omega t, right? Theta is equal to omega t. So if the omega is constant, and then how many seconds is it? During the 2-minute cooking period. So 2 minutes, 1 minute is 60 seconds. That's the theta, right? So 120 times that. 120 times 0.628. $75.36 radians. But then they want to know what is the total distance traveled by the fly. Well, then you go from S is r theta, so then you multiply this by the radius of the plate, 0.15 meters. You see? So all of these problems are showing you some manipulation of these equations, variety of that.
I have a question.
Yeah.
Is the fly gonna explode inside?
I was waiting for that question. Well, what happens to the fly?
Um,
Well, all of
So
the,
it's
See here, that's the fly right there.
all the water would be,
Yeah, I mean, there's
Microwaves.
water, right?
What, the microwaves would heat up the water inside
Yeah.
the fly, any human.
And then, yeah, I think it'll explode,
Yeah.
Okay,
From
good.
the
So now,
inside out,
let's go to rotational kinematics. So now let's go to rotational dynamics. So, in other words, to get to rotational dynamics, they're starting with Newton's law, F is ma, then they're taking the cross product of R crossed into F and R crossed into A, right? So they're saying apply the cross product. So if I'm trying to turn something, I'm applying what's known as a torque on that, right? So imagine taking a ruler, fixing this pivot point, and applying a torque on it, and I'm turning it. So how do I apply the concept of F is ma to a rotating object? You see, that's the idea. So then, you take an object. You could put the pivot point anywhere you want. So that's called pivot point. So that means I hold it here. You see? Then I go like this and apply a force on it, let's say like that, at a certain point. See? So I'm going to cause the object to accelerate, right? But since I have a fixed pivot point, it's not going to move. It's not going to have linear acceleration. It's only going to have rotational acceleration, you see? Goes like this, because I pivoted it about a point. So I apply a force. So what would Newton say about this? I don't know. Did Newton write about rotational dynamics? Probably as applied to planets he did, but I don't know about rods and all that kind of stuff. I don't know if he developed it that much, you know? So then, of course, Newton would start with F is ma, but then to be more exact, we have R, which is the vector from the pivot point to there, right? Take the cross product of R and F, then therefore I have to take the cross product of R and A, right? So then you start with Newton's law and you transform Newton's law to an equation of torque, you see? So then you say here, R crossed into F, M R crossed into A, but then what's A? Well, we just learned that A is alpha R, right? Remember the equation, this one? A is equal to alpha R, right? But to be more exact, these are vector quantities, right? A is R crossed into alpha. This is actually a vector quantity, you see? And A, which direction is the acceleration? Which direction is it? When you're going like this, the A tangential is this way, right? Right? Which direction is the R vector? To the right. So which direction is the alpha vector then? Alpha is the angular acceleration, but in reality it's actually a vector. Which direction is it? So if R is this way, alpha would have to be out of the board or into the board, right? So alpha, let's see, if it's rotating this way, alpha is out of the board. See? We're using the right hand rule. Because if something is rotating counterclockwise, you take your finger and curl it in the direction of the rotation, and alpha is the vector out of the board. Let's see here. Alpha is a vector out of the board. R crossed into alpha, no, that's going to give me into the board. So, yeah, A is alpha crossed into R, not R crossed into alpha. I did it wrong. Alpha crossed into R. So alpha is, it goes like this. Alpha is out of the board. R crossed into, no, sorry. Alpha is out of the board, so out of the board, crossed into R, that gives you like that, right? Cross product of alpha out of the board. So basically I could put alpha here at the origin. Alpha crossed into R, A tangential, so that's this. So then they're replacing this guy. They're replacing A by alpha crossed into R. Right? R crossed into alpha crossed into R. Right? Then what's that equal to? Alpha R dot R minus R dot alpha. What equation are they using for that? Is that something from Calc 3? Cross product into the cross product. The cross of the cross. That one I don't remember. I think it's probably something, some theorem about cross products. Theorem Does it come from somewhere here?
Theorem 2. No?
Like I crossed into J, crossed into J.
No, I think it's that top part. Theorem 2.
Did I put it? Where?
Theorem 2, right there. Theorem 2.
Oh, theorem 2?
Is it down?
Oh, yeah, yeah. R crossed into, yes, yeah. U crossed into V, crossed into U is U dot W times V, right? Because this is going to be a scalar times a vector minus a scalar times a vector. So then that's going to give you a vector. And then this is the proof of it. It's probably not that long of a proof, yeah, just one line. So then that's going to give you how do we do it? We do this dotted into that, right? So that means this guy dotted into that times this vector minus this vector dotted into that times that vector. Then what's that going to be? R dot into R is what?
It's like 2 squared.
That's just R squared, right? Because cosine, R squared cosine 0. So R squared alpha minus, what's R dot alpha? R, and then alpha is out of the board. So R dot alpha is 0. They're perpendicular to each other. The dot product of two vectors perpendicular to each other is 0. This disappears. Ah, that's where moment of inertia comes in, mr squared, right?
Why are we crossing them?
Oh, because the torque, the definition of torque is R cross into F. That's going to be the next step.
Okay.
So then they're going to say, you see
Yeah.
what happened here? You have m alpha R squared, and then R dot out, that came out to be 0. And then R crossed into F is mr squared alpha. And then R crossed into F is defined as torque. So the net torques on the system is equal to this quantity, mr squared, which we're going to call moment of inertia, mr squared, times alpha. So that's the Newton's version, Newton's law version related to torques, right, to rotation. So F equal ma gets replaced by F equals ma gets replaced by torque is I alpha, where torque is defined as the cross product of RF. So that's the definition of torque. R crossed into F, which is going to be what? Magnitude of R, magnitude of F, times sine of the angle between them, right? And then what's the definition of moment of inertia then? Definition of moment of inertia is going to be mr squared, right? You see? So naturally, therefore, the units of moment of inertia are going to be kilogram meter squared, kilogram meter squared. So what is the physical meaning of moment of inertia though? What is its use? Okay? Well, it must have the same use as what uses M had when you said F is MA, right? What was the use of M?
Counteract
M
the
tells you,
speed.
yeah, it's your inertia, right? It's how, M is a measure of how hard it is to accelerate you.
Like a resistance.
A resistance to a change in motion, right? Well, I is a resistance to rotation. It's how much an object resists being rotated, you see? Whereas this one, how much an object resists being moved, you see?
So let's say this was like a board with a fulcrum point in the middle.
Yeah.
You would just kind of do the calculations on like kind of figure out if it would like.
Yeah, well,
Like,
the
I
next
guess these
question is going to be, how do we apply this equation mr squared to more complicated object, okay? I can understand if it's just one small object with a mass m and a string, then its moment of inertia would be mr squared. But what if it's a board? What if it's a sphere? How do I find its moment of inertia? You see? So the equation mr squared is too simplistic for more complicated objects. Well, then you either use the summation format or the integral format, just like you had summation and integral format for center of mass. You see? So let's put the center of mass equation back on. X sub I, m sub I over summation of m sub I. And then the integral format of this is x dm over integral dm. But now we have moment of inertia. Summation format is m sub I r sub I squared, or the integral format would be r squared dn. So you see they're calling it moment of inertia, the rotational equivalent to mass. Summary. Where was I here? Practice. Well, before we get to that, let's see here. Let's open up another one. Now let's focus on moment of inertia. Moment of inertia. A quantity expressing a body's tendency to resist angular acceleration. You see? Pretty well said. It is the sum of the products of the mass of each particle in the body with the square of its distance from the axis of rotation. But then what if the object looks complicated? So there's all these kinds of moments of inertia diagrams. The moment of inertia of a hoop, and you're trying to rotate it around an axis going through the center. It's mr squared. That one you don't need to do integral. Why? Because the hoop is all equidistant from the axis of rotation. Right? So its moment of inertia is just going to be mr squared, because all of it is equidistant. You see? So that's the easiest one. Hoop. Moment of inertia is mr squared. The other kind of object whose moment of inertia would be mr squared would be just a point mass having almost no dimension attached to an end of a string about a pivot point. And then let's say this distance was r. What would its moment of inertia be? Again, mr squared. Write that. So a hoop and this is the easiest equation you can imagine. You see? Okay, then you get to the this hoop, but with a certain thickness, right? Annular cylinder. So then you need to do half m r1 squared plus r2 squared, right? So the R1 is the inner radius, R2 is the outer radius. Half m R1 squared plus R2 squared. We can see if this answer makes sense by doing what? What if the inner radius R1 was equal to R2? What would that become? If R1 was equal to R2, this object turns into a hoop, right? So then what happens? R2 squared plus R2 squared, right? So I is equal to r2 squared plus r2 squared, and then I becomes what? mr2 squared. You see? So this equation, a hoop is a limiting case of a cylinder of a thickness where the inner radius becomes closer to the outer radius, right? And then the moment of inertia becomes that, mr squared. You see? Then you got the solid cylinder, which is another limiting case of that. Set the R1 equal to 0. You see? If you set the R1 equal to 0, what's going to happen? R1 equal to 0. So then this disappears, and the moment of inertia becomes half m R2 squared. Right? So then that turns into a solid cylinder. Right? But then you can take the, go to the next easy one is to go to a rod whose radius is very negligible. So skip this one for now, go to a rod. And then rotate it about an axis going through its middle. You see? 1/12 ml squared. Moment of inertia becomes 1/12 ml squared. Now notice that the form of the moment of inertia equation always remains mr squared or ml squared. The only thing that changes from object to object is the coefficient in the front. The 1/12 or the 1/2. In the case of a sphere, it's 2/5. Right?
Where do those come from?
Yeah, exactly.
Okay.
You're gonna see where those come from in the next. We're gonna have a separate lab on it too. So 1/12 ml squared, right? And then the next one is gonna be the solid sphere, about an axis going through its center. Solid sphere, 2/5 mr squared. Then hollow sphere, 2/3 mr squared. Then the ones that are, this one is a extension of this one. It's a more general version of this one. I think that's what you were probably mentioning, the board, right? Because this thing is just an elongated rod, right? So it's 1/12 m a squared plus b squared, right? So if the a goes to 0, what happens? Then you just have b squared left over. You see? So a slab is just like an elongated two-dimensional rod. We call that slab. LW, moment of inertia, 1/12 m L squared plus W squared. Okay? So you see you're taking this y and extending it. Let's see. Now the ones that are kind of weird are this one. You go to a hoop, but instead of rotating it around the axis going this way like that, here you rotate it this way. It's like taking a coin, right? A coin can go this way, or you can flip it and have it spin like that, right? So this is, you're going this way, and then that one you're going this way. So moment of inertia of this one is half mr squared. See? So it's the hoop, but you're cutting it like that. So moment of inertia is half mr squared. So which one is it easier to rotate a hoop? Is it easier to rotate it like this or like that?
Yeah.
This is half as easier, or we should say twice as easier. Because when the moment of inertia is smaller, it means it's easier.
Why don't they do windmills like that?
There's actually wind turbines that go that way.
Oh.
Yeah, wind turbines. They're made like this, like almost a figure eight, I think.
Yeah.
And they go like that.
Right,
Yeah, it's better. It's easier, much easier.
Yeah.
You will spin twice as fast.
yeah.
Yeah. So imagine doing a figure eight.
Oh, okay. Oh,
Yeah, they have
Like
those
this.
things like in the park sometimes too.
yeah.
Yeah.
Oh,
Yeah.
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 Yeah?
Yeah, they're just like
Just for
public
toy.
art, yeah.
Yeah,
Oh,
But
I
they're,
see.
ro-
Yeah.
they're,
Like
they're
decoration.
shaped like that. And
Yeah.
they rotate.
Yeah. Nice. So yeah, this is gonna be twice as easy as this. Then you got this one, which is taking the rod, but now giving this a dimension. So making the radius bigger, thicker, you know. So then you got, so you have like this one here, and going like this. But now you have you can't ignore this anymore because it has a big radius. So what's the moment of inertia of that one? Well, you got this one, 1/12 ml squared. You see? So this one, 1/12 ml squared, 1/12 ml squared. That is still there. But then you got this extra quarter mr squared, which is, okay, you know where this is coming from? You're taking, notice how this is half of that, right? And then so now this one, if it's solid, look, if it's solid, you take that, break it in two, this should be half of that. You see? Just like this is half of that, this should be half of that. So since that's half of r squared, half of that is a quarter. You see? So this is to that as that is to that. You see? So then you're taking a quarter mr squared, which is half of that. Right? So we could also add more to this. You could say, imagine if the L was negligible and it was just a solid coin. Right? Then what would its moment of inertia be? Then the L will be negligible and it would disappear. Then you would just have quarter mr squared. You see? So you can bring more shapes. I don't know if any of these tables give you more. Those are the common ones that we have. I think they're all giving the same ones. A hollow sphere, solid cylinder, hoop, hollow cylinder. Okay, but now where do those come from, as Alan was asking? Well, to derive them, you have to use the integral version of the moment of inertia to derive all of these, where these guys are coming from. Okay? The simplest to do is, let's do the rod first. Then we can learn to do the sphere and the cylinder. So the rod is the simplest one because it's more one-dimensional. Oh, you know what? This one didn't give. They should have given the moment of inertia of a rod about its end axis. That's a common one. They forgot to give that one. No. 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 None of those have it. There you go. This one. You see? They forgot to give that one. The moment of inertia of a rod about its axis around the end, right? So in other words, if I'm going like this versus going like this, you see? Pivoting around the end like that, like this. So this is 1/3. I center of mass of rod, 1/12. I end of rod, 1/3. So let's derive the center of mass, right? So then you take a little piece of this. So then I'm going to use this form of the equation. I is equal to integral r squared dm. So you're going to take a little piece of it and you're going to say, how much moment of inertia does that piece have? And then let's sum up the moment of inertia of all the pieces, right? So di is the moment of inertia of that piece, which has a mass dm, right? So then its moment of inertia is going to be x, right? Its distance from the pivot point squared, right? So x squared times its mass dm, okay? Then I'm going to define something known as linear mass density. Linear mass density, which is dm over dx, right? So that tells you the density of the rod in units of kilogram per meter, or gram per meter. So then I can say dm is equal to lambda dx. Okay, then I'm going to have here di is equal to, or I should just say, di is x squared dm, so then x squared dm is going to be lambda dx. Then I can integrate this along all the pieces to get the total moment of inertia of the rod. So for today, I'll deal with things that are uniform mass density. Their mass density does not change as a function of the x, right? So the material is made of the same material all throughout the rod. So the lambda will come out of the integral. So then you'll integrate x squared dx. Then you'll go from negative L over 2 to L over 2, right? The L is the total length of the rod. So then that's how you derive the equation for moment of inertia, right? It's always with that kind of a step. So x squared dx, then you're going to have, we could use the fact that this is an even function, so you can integrate 0 to L over 2 and double it. And then you integrate that, you get what? X squared over 3.
X cubed.
Yeah, sorry, x cubed over 3, 0 to L over 2. Then you get 2/3 lambda. Then you get here 2 L over 2 cubed. L cubed over 8, right? Then you're going to have here lambda L cubed over 2 goes into 8 4 times 12, right? So L over 2 cubed, 3, let's make sure we did that all right. L cubed over 8, 2 goes in 4, 4 times 3, 12, lambda. Then you want to get rid of lambda, so then you integrate dm is lambda dx equation. So then you want to express lambda in terms of the mass of the rod, right? But if it's a uniform mass density, lambda comes out of that integral also. Then you get integral lambda integral dx equals integral dm, right? And then integral dx is just the length of the rod, and then integral dm is just the mass of the rod. Therefore, lambda is just m over L, if it is uniform. You see? So lambda is m over L if lambda is uniform. Then you can replace that here. Okay, there you go. We have proven this one. Now, 1/12 ml squared. Right? Now, how do we prove that one? The axis at the end. Can I do another integral?
You just change the limits of integration?
Yeah, just change the limits of the integration. Just go from 0 to L, instead of negative L over 2, to L. Yeah,
For the integral with lambda dx,
yes.
so for the L would be the antiperiod of 1, right?
The integral of dx?
Yeah.
Yeah, it's just, the integral of dx is just x, and then you're going from 0 to L, 0 to n. Yeah.
Don't you have 48 for that L cubed over 48?
48? No, it was actually just 8.
Oh, you simplified.
And then what I did is the 2 divided into 8 4 times.
Yeah, okay.
Yeah. Okay, so now the only difference is now change this to lambda, change it to m over L, but then go 0 to L. Instead of going negative L over 2 to L over 2, you're going 0 to L on this integral. It changes it a lot. Because then instead of going 0 to L over 2 and doubling it, you're not doing that. You're not doubling anything. You're just going 0 to L directly. So now you're going to have x cubed over 3, 0 to L. Right? So therefore you have ml squared over 3. So which one's harder to rotate? Rotating a rod about its center or rotating it about its end? Well, you can test it now with your fingers. Try to do this with your finger with the pen versus try to do this.
That's
Which one
harder.
feels harder?
This is harder.
The end is harder?
N is harder.
Yeah, it should be. How many times harder? How many times is this bigger than that?
4 times.
4 times, right? 4 times that gives you this. So this should be 4 times harder to do. So the pain on your face should be 4 times more. Versus
And then,
this one is smile. Okay. Same thing with any uniform rod. This is 4 times easier than that. You see?
yeah.
And that's what you're saying this integral is, right? From the end?
Yeah, from 0 to L. Yeah.
With my pen like this. And then
You wouldn't really know that if I just had asked you how many times is this harder than that. You would either have said, I don't think they're harder, or you might have said, this is maybe twice as easy as that.
Right here.
You would have thought twice. Where did the 4 times come from? Well, something having to do with the integral. This one came out 3, and this one came out 12. Came out 4, some magical number, 4 times harder. Okay, how about if the axis had been some other axis? That means I could take a rod and go halfway between the end and the center. Now what's the moment of inertia? So then I can go the integral would be what? Negative L over 4 to what? 3/4 L. You see? But is there a theorem that I could use so that I don't need to keep integrating for every point? You know? You know what I mean? So, in other words, if the axis is here, if the axis is there, if the axis is there, if the axis is there, here, here, is there something I can do where once I know one of these, I could do something and I don't have to keep integrating? And the answer is, yeah. Physicists always look to make life easier, except during tests. Right? So that's called the parallel axis theorem. This is the moment of inertia of shape about a point O. Moment of inertia of shape about its center of mass, centroid. Added moment of inertia due to the distance between O and C. In other words, If you already know the moment of inertia about an object, about its centroid, which is its center, right? And if I want to shift it by any distance, I don't necessarily have to shift it to the end. I can shift it to some weird distance, right? Then all I need to do is just shift it up by md squared. And d is the distance between the centroid and that point. You see? That way I don't need to keep integrating. All I need to know is the moment of inertia about its center of mass. So I about any axis is equal to I center of mass plus md squared. So in other words, could I have applied that to this, to the rod? Yeah, I could say, what is the moment of inertia of the rod about the end? What's the moment of inertia of the rod about its center? 1/12 ml squared. What's the shift amount from the center to one of the ends? It doesn't really matter which end in this case, right? So what's the distance d? So here's the center of mass. The distance d is from the center to one of the ends. See, that's d here. So in the case of the rod, the distance d is L over 2, right? L over 2 squared, right? So then what's that going to be? (1/12 ml squared plus 1/4 ml squared. If we do that right, it should give us what the integral gave us, 1/3 ml squared, right? So therefore, I don't need to keep integrating. You see? So multiply this by 3, multiply that by 3. What do we get? 3 plus 1 is 4. 4 over 12. 4 over 12 is 1/3. You see? So if I want to, in that case, let's say a cylinder. Let's say the shape is a cylinder. The axis is coming, which one are they doing? Let's see here. That's my problem. Oh God, I'm on Google.
You found your own work?
Huh?
You found your own work?
I found my own work right there. Let's see here. Oh, they took the hoop in this case. They took the hoop. Remember the hoop we said was the easiest? Going through it here. So what's the moment of inertia of that? We said, remember it was mr squared, right? But what if the axis is like this, through one of the ends? That's what they're doing there. No, I think something is wrong with this one.
Okay, no.
It should be mr squared, then you should add, I don't know why they're saying half m. That's probably the cylinder. Yeah.
I know, like on vibration motors, it's almost like a hemisphere. Like it's basically a cylinder like this attached to the rotation, and when it's spinning, it causes like your phone to vibrate or whatever. That's how they get that.
Oh, the vibration on the phone?
Yeah, it's like I've seen motors like that where it's just
Inside
like,
of it.
Yeah.
Ah.
And as it's spinning, it's causing it to. Every revolution causes it to. So I've noticed that, which is kind of like that, except that's a full sphere.
So for what would the hoop be? If I was taking the hoop and going at the center, I mean at the edge right there,
The age is,
then I would go. This is the moment of inertia about the center, right?
yeah, that's the center.
Then I would shift that by md squared, and the d would be the distance from the center to the edge. right? And then what would the distance be? That would be the radius. So it'd be mr squared plus mr squared, 2mr squared.
You're saying this is wrong because they're saying that
I don't know why it's they're
Half
saying
mr
half
squared.
mr squared there. I think it's something else. It should be 2mr squared.
There's something right in the corner. Maybe they were trying to do a different problem.
See ICM, and then go D. So if I try to rotate this about this axis, then I have to do ICM plus ND squared. See? Let's see, where's the proof of the, yeah, this is a pretty good one. I equals ICM plus MR squared. So once you know what the ICM is, then you don't have to need to integrate in the other place. You just shift it by MR squared. You see, it's such a good, useful law. Okay, so now we know how to do rod, and we know how to do the center of the rod, and then shift it to anywhere using the parallel axis theorem. Okay. How about cylinders and spheres? Moment of inertia of a cylinder. Okay, so then I'm going to say the moment of inertia, I'm going to take a cylindrical shell, right? I'm going to say the moment of inertia of that, di is equal to r squared dm, and r is the radius from here to here, right? And dm is the mass of that cylindrical shell. Cylindrical shell. So then I'm going to define the volume mass density rho, which is dm over dv. Therefore, dm is equal to rho dv. Then I'm going to substitute that into there. I is equal to integral r squared rho dv. So then what happens? I'm again going to do uniform mass density. So the rho comes out of the integral. Then you have r squared dv. So the rho of uniform comes out. Then dv is going to be the volume of a cylindrical shell. What is that? Volume of a cylindrical shell.
I mean, it's a solid cylinder.
Yeah,
It's a solid cylinder.
solid cylinder.
It's not hollow.
No, if it was hollow, it would just be mr squared, the moment of inertia. I wouldn't even need to do an integral.
Yeah, right.
Yeah, it'd just be mr squared.
MR squared.
But if it's solid, then you need to integrate.
What if like the hollow part of the cylinder is like very tiny? It's not. No.
If you mean the hole inside is
Yeah.
tiny, well, you could do here integral from, let's say, R1 to R2. Remember the equation that we had for this kind of a cylinder was what? Half m R1 squared plus R2 squared. So depending on what the inner radius of the hole is, that's the general equation for the moment of inertia of any cylinder. If R1 is 0, then it's just half m R2 squared. So right now I'm doing a closed cylinder, but if it's hollow, then you can just put an R1 squared. Yeah. Okay. So then what's the volume of a cylindrical shell, dV? It's going to be 2 pi r, the circumference of the shell, times the thickness of the shell, right? So 2 pi r times the thickness times the length of the shell. 2 pi r dr times L. Okay? Then the constants come out of the integral, 2 pi L comes out. Then you go r cubed dr. So if you want to do the most general case, like he's suggesting, a cylinder with a hole in it, I can now calculate from R1 to R2 instead of 0 to R2. That will give me the general equation. Right? So then that's going to be I is, what is that? R4 over 4? 1/4. R2 to the 4th minus R1 to the 4th. So this is from the inner radius R1 to the outer radius R2 of the solid cylinder. Right? R1, R2 to the 4th minus R1 to the 4th, 1/4. And then 2 cancels the 4, so I get I is equal to pi L rho over 2. R2 to the 4th minus R1 to the 4th. But then I have to get rid of rho, right? What's rho? Then I integrate this guy. Integral, what? Rho dv, because rho is uniform, it comes out of the integral, right? And then rho v. So therefore, rho is the mass of the cylinder over the volume of the cylinder, right? Rho is m over v. Then I substitute that there. Okay? What's the volume of a cylinder, which is a hollow cylinder? What's the volume of that? It should be pi r2 squared minus pi r1 squared over times L, right? That's the total volume. So volume is pi r2 squared minus r1 squared. R2 to the 4th minus R1 to the 4th. See what's going to happen? I love it. Pi guys is pi m L over 2. Oh, I forgot the L, right?
Yeah.
The volume is pi R2 squared times L. So the L should cancel.
And R2 squared plus
And then this is
R1
R2 squared minus R1 squared, which cancels with that. Then you got R2 squared plus R1 squared, right? A squared minus B squared is A minus B, A plus B, right? So A to the 4th minus B to the 4th is A squared minus B squared times A squared plus B squared, right? So then you end up with R2 to the squared plus R1 squared, and that's the equation that was in the table, right? M over 2 R1 squared plus R2 squared. Right? So this is general. Now if there is no hole, then R1 is 0. And then this is gone. Right? So that shows you for the cylinder. Now how about a sphere? Sphere is trickier. Sphere is trickier. Why is sphere trickier? With sphere, let's say the sphere is rotating about this axis. The problem with a sphere is if I take a spherical shell, the moment of inertia of the spherical shell is no longer r squared dm, right? But with a cylinder, so imagine I take a spherical shell like this. Different parts of the spherical shell are closer to the radius of rotation, right? Their distance is not the same. So what do I do? Dang it. Thank God that somebody has done a video on this.
Does that make sense? Because
With a cylindrical shell, it's easy, right? It just goes like this, and then there's a line through it, and it's uniform distance. Then it's r squared dm.
but at the end it's just a point. And it's
You heard?
Yeah, yeah.
wider in
Feels
both
like everybody's
directions
done.
going around as it gets closer to this access point.
And now how do I find the video? Chapter 10. It should be somewhere here. This chapter has a lot of videos. Moment of inertia of sphere uniform. Moment of inertia of cylinder uniform. Non-uniform. So far I'm just doing uniform. Moment of inertia of sphere uniform. Okay, this one right here.
Every project you get involved.
To the moment of inertia of a sphere, we're going to treat uniform density sphere. We see with sphere that there's only one way of rotating it. You could rotate it around the z-axis, and that means the sphere is spinning this way. You could rotate it around the y-axis, which means the sphere is rotating this way. You could rotate it around the x-axis, which means the sphere is rotating this way, like this. But since the sphere is uniform, since it's identical in all three dimensions, all three are the same. It comes out that the moment of inertia of the sphere, all three of them are being equal. It's equal to 2/5 mr squared. So there's again two ways that we could prove this. One, we're going to use spherical shells with single integrals. Okay? Then we're going to use triple integral. Okay? So in order to do the single integral, here's what we have to imagine. We have a sphere. We have to imagine a spherical shell. Right? However, the problem with the spherical shell is that if you take an axis and cut it and it's starting to spin this way, the spherical shell is not uniform distance from that axis, right? So it's not like the cylindrical shell for the cylinder where everything was uniform. So here's what we have to do. We have to imagine as if the sphere is rotated around a point in the center of the sphere, which it really isn't. You can never rotate just around the point. You have to rotate around an axis. So we'll call that I or R, but it's an imaginary moment of inertia. It would be the moment of inertia if the sphere could rotate around that point. We can calculate the IRR pretty easily because the spherical shell will be uniform distance from that, right? So we can say DIRR is equal to R squared dm, and then we're going to integrate that. IRR is going to equal R squared rho dV, the volume mass density. So then you have IRR equals, since it's uniform sphere, the rho comes out. dV is equal to 4 pi R squared dr. That's true for any spherical shell. The surface area of a sphere times the thickness of the sphere. Then you do this integral. IRR is equal to 4 pi rho integral r to the 4th dr. And then you integrate that from 0 to big R. And then you have this integral is r to the 5th over 5. Okay. Then of course you put what the volume density is. Rho is equal to the mass of the sphere over the volume of the sphere.
So you see what I did? I'm assuming as if the sphere can rotate about its center point, which it can't, really. It can't. So I'm calculating an imaginary moment of inertia as if it could rotate here, because I want to use the equidistant. So 4 pi r squared is the rho, is the dV, and then this is r squared dV, right? Times rho. And then rho 4 pi integral, then this is r to the 4th. Then I'm going to calculate I'm going to put down what the rho is. Rho is the mass of the sphere over the volume of the sphere. 4/3 pi r to the 3rd. Then I'm going to get rid of that, right? 4 pi m over 4/3 pi r to the 3rd. R to the 5th over 5. Okay? then I'm gonna calculate what's known as
is
IRR.
4/3 pi r cubed. That's the equation for the volume of the sphere. You substitute that into the rho. Okay, so IRR is equal to 4 pi m over 4/3 pi r cubed times r to the 5th over 5. So what happens? The 4 pi cancels, the 3 goes to the top.
And then R cubed,
And r cubed cancels with that, r squared over 5. Then we use this theorems that says that the moment of inertia Ixx, which equals Iyy, which equals Izz, this is always equal to 2/3 IRR. Okay? So remember, IRR was just an imaginary concept, as if the sphere could rotate around its center, but it didn't really exist. So we calculated that, then we take 2/3 of that. We always take 2/3 of whatever we get for IRR.
okay, so once you get that, you're gonna use that theorem. Ixx is the true one that we're interested in. The moment of inertia around this particular axis, x, y, or z, right? Ixx is 2/3 IRR, no matter what the IRR is, right? So then Ixx is gonna equal what? 2/3 of 3/5. So the moment of inertia IRR of a solid sphere is 3/5. 2/3 of 3/5 is what?
2/5.
2/5. There you go. That's the moment of inertia of a solid sphere. So according to that, what would the moment of inertia of a hollow sphere be around the x-axis?
So if it is hollow, so it shift from R1 to R2.
Let's use this cheating rule again. Let's first calculate, assume the hollow sphere could rotate about its center. Assume. What would its moment of inertia be? All of it would be equidistant from that point, right? So IRR would be just mr squared, right? Now can we use the rule Ixx is 2/3 of IRR? Yeah. So the Ixx of the hollow sphere would be 2/3 mr squared. Was that the moment of inertia of a hollow sphere when we looked at the tables? Yeah, I'm shaking my head. Yeah, that was the moment of inertia of a hollow sphere, right? 2/3 IRR. Now, what if I don't want to use that cheating technique and I want to actually prove what the moment of inertia of a solid sphere is? How would I do it?
So Ixx therefore is going to be 2/3 of that.
Pretty much
Well, 2/3
the
of
same method.
3/5
Like you take the interval
gives you what?
of that, and then
Basically, that gives you 2/5, right?
get the answer.
2/5
You have to put it in
mr squared,
low.
and that would be the equation for the moment of inertia.
So maybe you could point it there now,
This is a solid sphere,
Alan.
okay?
Maybe you could point it there.
What if the sphere was hollow? What would happen? Like, let's say, a basketball, a tennis ball, something that doesn't have anything material inside. Well, if we use this method, if it's a hollow sphere, then there's nothing inside. So if we do a spherical shell, the spherical shell is only on the outside, right? So the IRR becomes r squared m. And since all of the mass is concentrated on the outside, there's no need to integrate. It's just r squared m. Then Ixx is 2/3 of that. Equals 2/3 mr squared. And this is actually the equation for the moment of inertia of a hollow sphere. 2/3 mr squared.
See?
The moment of inertia of a solid sphere is 2/5 mr squared. So if the two race down the hill, who wins? The solid sphere wins because 2/5 is a smaller ratio than 2/3, right? The solid sphere has the least moment of inertia between a solid and a hollow sphere, and it even beats the solid cylinder. The solid cylinder was half mr squared. So 2/5 is a ratio smaller than a half, and therefore 2/5 should win the
Right,
half.
so a car that
The
has
half should win the
spherical
2/5.
tires
So a solid
should be the
cylinder
car that
wins
is
the race
cylindrical
against the
tires.
hollow sphere, but it
Right.
loses to a
Down the race.
solid sphere. How about a hollow cylinder? Hollow cylinder, well, it's just basically everything is uniform, so it's just rolling, everything is uniform, it's mr squared, the moment of inertia. So this is the slowest out of them all. It's double the moment of inertia of a solid cylinder, and it loses to any of them. So again, you can go and watch the demos playlist and see some demos that I have on this section. So let's actually, now that we have the proven of the 2/5 and the 2/3, let's go and prove this with triple integrals, and we're going to perform the integral in spherical coordinates. Now we come to the spherical coordinate derivation of the moment of inertia of a sphere, which is 2/5 mr squared. We would choose our sphere like this, and we would have our axis spinning this way, and we would have the volume, a little piece of volume here. This is r, and this is phi, and the angle around, if it's like this, the angle around like this way, it would be theta. So we know from spherical coordinates.
So this
that
way
we
you don't have to use the
phi,
2/3 rule.
which goes from 0 to pi. It's the angle as measured from the vertical, and it goes all the way from 0 to pi. Theta measures the angle around this way. It goes from 0 to 2 pi, and of course r goes from 0 to r. Sometimes we also call that rho, okay? So the moment of inertia of that little piece is going to equal what? Its distance, this distance from the axis, the shortest distance. So what is that distance? Well, that is actually r sine of phi, right? So we don't want to know the distance exactly from the center. We want to know the distance from the z-axis. We call that the z. So that distance is going to be r sine of phi. So that distance squared times dm. Okay? dm is again going to be rho dv. So this is going to be xx, or it could be zz or yy. They're all the same for the sphere. Okay? So let's change it to zz, since we call that the z-axis, right? And we're going to have r squared sine squared phi. This is rho dv. Now what's dv for in spherical coordinates? dv in spherical coordinates is equal to r squared sine of phi dr d phi d theta. Now if we put that one here, we have d I z z r squared sine squared phi rho, and then dv is equal to r squared sine phi dr d phi d theta, and then we're going to integrate that, and the rho comes out of the integral, and then
Okay,
we
guys.
integrate that, and we
See
have
how
I z. Okay, so what does that equal to? So we actually have triple integral rho. Okay, so we have what? We could do the r integral, r to the 4th dr from 0 to r. Then we have sine phi d phi, and we have d theta. Okay?
Actually, it should be
So
sine
actually,
cubed.
no, we have actually sine cubed, right?
Yeah.
Because we
See, you
had,
heard
we
me.
had the sine of phi.
I love these
from,
videos. They're
distance,
interactive.
Which we squared.
Yeah.
You
Then we
talk
have
to
another
it, and then
sine,
you
so we
heard
actually
me.
have
Sine cubed.
Oh man.
Phi. Okay? So this integral here is going to be dz rho integral. So that, of course that's going to be r to the 5th over 5. Then we're going to have sine cubed phi d theta from 0 to pi. So if you do that integral, sine cubed phi d phi from 0 to pi, I'm not going to go through the steps of that. You could either do it with a TI 92 or any kind of TI, TI 89, TI 86, or any TI, or you could do it by hand. So it takes some time, but this integral, 0 to pi sine cubed phi d phi, comes out to be 4/3. It's just a number. There's no pi in the answer. So now we have I, Z, Z is equal to rho r to the 5th over 5. 4/3 comes out. Then you're left with integral 0 to 2 pi of d theta, which is the last integral of the triple integral. So that gives you 2 pi, right? At rho r to the 5th over 5 4/3 times 2 pi. Then the last thing is we put what the rho is equal to. Rho is the mass of the sphere over the volume of the sphere, which is 4/3 pi r cubed.
See, did I have to do anything about IRR, this imaginary thing? No. But it did take a lot more work. You see. So that's the other one is a nice shortcut.
This 4/3 is going to cancel with this 4/3, which came from the integral of sine cubed pi. This pi is going to cancel with this pi. R cubed is going to cancel with this, make it r squared. Then you're going to have 2/5 mr squared. So the moment of inertia ZZ is equal to 2/5 mr squared. With this way of doing it, spherical coordinates, we didn't have to use that theorem that says Ixx is 2/3.
It's nice
of
to see
IRR.
both.
We did it
So you can see,
from
oh, okay,
spherical
single
coordinates,
integral method.
and we got the same answer, 2/5
Triple
mr
integral
squared.
method.
With the other way of doing it, we first do it with a spherical shell, then whatever answer we get, we take 2/3 of that.
Okay. Okay, guys, good luck. See you tomorrow for the lab.
Uniform sphere.
And we'll continue from there. Next.
Kiledjian